All right, perfect. Good morning, everybody. Welcome to another session in the ML Ops World conference. And today I bring to you a topic called, is your ML model trustworthy? And this is an awesome topic because we all face the challenges of putting machine learning in production, where we build awesome models, it's great accuracy, everything's working, but somehow the adoption of that model and for business users to accept the results becomes challenging. And you're building explainability tools and you're bringing in dashboarding and other capabilities to actually get them to the point where they can accept your results. So today we have María Grandury to talk us through this topic. So María happens to be a machine learning research engineer at a startup called neurocat. Her areas of expertise are NLP, AI robustness, and explainability. She has dual degrees in mathematics and physics, which is exciting for me because I feel like machine learning fits so well between mathematics and physics. And she also happens to be the founder of the Hugging Face community of Spanish-speaking NLP professionals. And she also happens to be the core team at Women in AI and Robotics. So I'm very excited to have María, a fellow women machine learning engineer, present today. María, please take it away.
Hello. Thank you, Kanchana, for the introduction, and thank you, everybody, for joining the session. I'm very excited to dive into a topic that, in my opinion, is very, very important and actually right now is getting more and more traction. So as mentioned, I'm currently a research engineer at nuerocat, and we are developing a toolkit to assess the quality and trustworthiness of machine learning models. And to do this, we distinguish three quality pillars. The first quality pillar is functionality. In the functionality pillar, we find all the analysis related to the performance of the model. So let's see how the flow of a model looks like until it goes into production. So usually first we get the data, then we train the model with it, and then depending on the task we want to address, we measure one or more performance metrics. So for example, if we have a classification problem, we could use the accuracy or the F1 score. And if we're tackling a regression problem, we might use the mean squared or absolute error. If it's a ranking problem, we can use the mean reciprocal rank. For NLP tasks, we have bleu or rouge scores. And for GANs, we can measure, for example, the inception score. Okay, so once we have measured our metric or metrics, if we are not happy with its value, we can retrain the model with, for example, more data or different hyperparameters. But what happens if the value of the metric is high enough? So should we deploy the model directly? And sadly, this is usually the case. Of course, choosing the right metrics is crucial for the evaluation of a machine learning model, but the performance metrics are not the only ones that should be checked to assess the quality of a machine learning model. So the important question is not, is my performance metric high enough? The question you have to answer to deploy your machine learning model is actually the title of this talk. Is my machine learning model trustworthy enough? So now I'm going to show you how to actually be able to answer that question. So I used to love a lot of this meme at university with some professor would say that the demonstration of a theorem was trivial. But actually, I think that it represents quite well what's happening right now in the AI field. So of course, it's really nice that we have every time more complex models and architectures that allows us to solve a lot of different tasks and with really high accuracy. But the problem is that we have no clue why they work, why they are so accurate, and why do they predict what they predict. So to answer these questions, we need the second quality pillar, that is explainability. So the XAI field, or explainable AI field, includes all the techniques that try to open the black box and try to explain that miracle that happens, enabling us to interpret the decisions of the AI models. So they basically explain the output of the model with respect to the input. And what we want to do is check which of the input features had a bigger impact on the prediction. So yeah, okay, now you might say, yeah, of course, it's nice to know why a model predicts something or another thing, but yeah, this might be really nice for researchers or yeah, geeks like Maria, but do I really need it? Do we all need it? And the answer is a big yes. So explainable AI is crucial in a lot of fields. For example, if we take AI in healthcare, let's say a model to perform diagnosis, just imagine you go to the doctor and the doctor tells you, well, look, you have this disease and you need to get surgery. Why, right? You would like to know why. So imagine that now the doctor tells you, well, I'm not sure, but the machine learning model told me so. So I guess, yes, you need to get surgery. It's really not the explanation you were expecting, right? We can also take another example. So for example, imagine that now you're training a machine learning model that is going to be used at a lab to decide which molecules should be synthesized to create a new drug. So you're going to go to the lab and tell them to invest thousands of euros or dollars to develop a new drug. And you need to convince them to invest all that money in one molecule, but not another one that is really similar, and all that without any reasonable explanation. So yeah, well, good luck with that. And this applies to a lot of other use cases. So if we need, if you need people to trust your predictions, if you need people to invest in your model, then you need to be able to give them an explanation. So yeah, how do we do this? How do we explain the predictions of our model, and which are these explainability techniques? One of the most famous explainability methods is SHAP. SHAP was introduced in 2017 by Lundberg and Lee in the paper A Unified Approach to Interpreting Models' Predictions. And it is a method to explain individual predictions, and it is based on the game theoretically optimal Shapley values. So what SHAP does is it explains the prediction of an instance called X by computing the contribution of each one of the input features to the prediction. Yeah, so to fully explain how SHAP works under the hood, I will need a whole session, I think. So what I'm going to do is show you how easy it is to use the Python library and explain to you with some examples how to interpret the output plots. And then if you want to deep dive into this technique, I can point you to some resources. So as I said, the explanations that SHAP returns show how each of the input features contribute to push the prediction of the model from the base value. And we define the base value as the average prediction over the whole training data set. Okay, so in this case, well, in all the SHAP plots, if a variable is red, then it means that it pushes the prediction to a higher value. And if it's blue, then it means that it pushes the predictions to a lower value. So here in our first example, we are going to explain tabular data. We explain a regression model trained on the Boston housing dataset. We see that the two variables that had a bigger impact in the actual prediction were the LSTAT, that is the percentage of lower status of the population, and it's red. So this means that it pushed the prediction to a higher value. And the second one would be RM, which is the average number of rooms per residence. And this one is pushing the value in the opposite direction because it's blue. So this way we can just see how all the input features of the model actually affected the output value, the final output value. Okay, here we see another way to visualize the explanations using what we call a force plot. This plot was introduced in the paper Explainable ML Predictions for the Prevention of Hypoxemia During Surgery. And the second example is a text example. So we took a transformer from the Hugging Face library. We trained it on the IMDb movie review dataset for sentiment analysis, and then explained the sentence, "What a great movie if you have no taste." So here we can see that what A is kind of pink, so it pushes the prediction to the right, so to a higher value, but not a lot. It doesn't like influence the prediction a lot. But great movie, of course, it sounds like a very positive review, right? So that's why it's so red. And also in the force plot, we see that it goes from 0. Let's say 5 till almost 882. But if we finish there the sentence, then that would be the prediction. But then we add, "if you have no taste." So that is in blue because of course it tells us that the sentence was actually sarcastic, and we see that it actually pushes the prediction again to a lower value. So finally, let's see what we do for image data. So here we see an explanation of a set of images from the MNIST dataset of handwritten digits. In the plot, we see 10 outputs, so they correspond to the digits from 0 to 9 for 4 different images. And as before, the red pixels are the ones increasing the model's output, while the blue pixels decrease the value of the prediction. So we can see that for the 0 image, the blank middle is important because, for example, if it was the same shape but the middle wasn't blank, then it could be an 8. So it really checks that the middle is empty, is white. While, for example, for the 4 image, we also see that it pays attention that there's no connection on top that would convert the 9 into the 4 into a 9. Okay. So the third quality pillar would be robustness. And let's take some examples to see why this quality pillar is also very, very important. So if we take, for example, an autonomous car, just imagine you bought an amazing autonomous car, but the day is kind of, foggy, and the accuracy of the computer vision model falls to 50%. Would you be happy? I don't think so, because it's really dangerous. Or what happens if it doesn't understand a stop sign because there are some stickers on it? Or what happens if it's snowing and one of the multiple sensors that all these cars have then fail, and it just outputs a constant value all the time? So in those cases, your life and the life of the people around depend on the car. So we really want that model to be robust. Those are all examples for images and tabular data for the sensors. But for example, when it comes to text, what we want it to be robust it like against to is, for example, typos or synonyms. Because if you write an email or an application, you don't want it to end up in spam or something worse just because a single typo, right? So, okay, let's see how we can avoid this kind of errors. All the examples I said before are natural examples that can confuse our machine learning models. But now we're going to introduce a new concept that is adversarial examples. And these examples are inputs to the model that an attacker has intentionally designed to cause the model to make a mistake. So research in 2013 in this paper that I cite here, Intriguing Properties of Neural Networks, show that neural networks are actually vulnerable to these adversarial attacks. So at the beginning, these original adversarial attacks were small and well-chosen perturbations to an image, and then they fool the image classifier. So yeah, as you can imagine, adversarial examples caught the attention of a lot of researchers around the world. And since 2013, there has been a lot of research papers published tackling these issues. So one of the first papers that was published was the FGSM attack. And this attack is, well, the fast gradient sign method attack. It was proposed by Goodfellow, Slengs, and Szegedy. And it basically computes the gradients of the loss function with respect to the input image. And then instead of minimizing the loss, it maximizes the loss. So the result is an output image that for us humans looks really identical to the original, but for the neural network is just a totally different image, and it makes it predict it in an incorrect way. So since the FGSM attack, there has been, yeah, as I said, a lot of more sophisticated adversarial attacks, and also some defenses. So the defenses are, procedures for training neural networks that are resistant against adversarial attacks, and that makes our machine learning models more robust. A nice library for adversarial attacks and also defenses is the CleverHans library. So this library provides implementations of adversarial examples, how to construct them, and also some defenses. So the main contributors to it are Papernot, Fagby, Carlin, and Goodfellow. And they have, as I said, both adversarial attacks like the FGSM attack and the Carlini-Wagner attack, and also defenses like resampling. Moreover, I would also recommend to check their blog about AI security, because they have really, really interesting posts. So that library is valid for images and tabular data. And now we're going to see another library that is valid for text attacks. So the library is called TextAttack, and was published, is explained, let's say, in the paper TextAttack, a framework for adversarial attacks, data augmentation and adversarial training in NLP, and was published last year. So the library, as all the ones I have mentioned before, is open source and really easy to use. So the example we're seeing here is the application of a text attack to an LSTM trained on the Rotten Tomatoes review, movie review. So also a sentiment classification like the IMDb dataset. And here we are using the attacks deep wordback and text fooler. And we see that there are two types of adversarial examples for NLP. So one way to trick the model is to have an example that is visually similar. So for example, you could just delete a character or change a character or add one. And here in the example, we see that just deleting a C at the beginning, the prediction swaps from positive to negative at 52%. So that's a lot. And the other type of adversarial examples is when the actual meaning of the sentence is similar. So they are semantically similar. In this case, it changed film by footage, and it also makes the prediction of the model change. So in CleverHans, we said that there were also defenses. And another way to make your machine learning model more robust is using adversarial training. So this is basically taking adversarial examples and retraining your model with them. And is of course valid also for text. So it's valid for all the, it's valid for text, tabular, and images. Okay, nice. So now we know the 3 quality pillars. Remember, they are functionality, explainability, and robustness. And now, what do we do with this information? So since we're at the MLOps World Conference, let's see how we can automate this and integrate it into our MLOps workflow. So nowadays, there are a lot of tools to organize the flow of the machine learning models before they go into production or also production. For example, we have MLflow, Airflow, Neptune, Kubeflow, MLrun, and actually during the day of today and tomorrow, there's going to be a lot of talks about this. So be sure you check them. And what I actually suggest is adding just one step just before the deployment of the machine learning model to check the quality. So the idea is that the quality check would act as a switch. The switch that we were talking at the beginning, if it was just about the accuracy or the performance metric. So now we would compute a score mixing the the performance metric, the robustness score, and the explainability. And with that, then we would be able to say if our machine learning model is actually trustworthy and ready to be deployed. Thank you very much.
Fantastic. Thank you, Maria. It was a great presentation. There are, I think, a couple of questions on the chat, and maybe we could start with that. There's a question from Pablo, and his question is, could SHAP be used for a classification model? I almost feel like you had an example of that in your slides, didn't you?
For what? Excuse me?
Could SHAP be used for a classification model, for explaining classification models?
Yes. So let me go back to SHAP. So, okay, this is a regression, but this is a classification model, actually, or this one. Actually, if you have a classification model, then in the output node, then just going to classify it. So basically what it does is for each neuron, it just pushes the prediction or to a lower value or to a higher value. And I don't know if you want more specification about this, because I already talked about classification models. I also have some snippets of code at the end of the presentation. I have some slides if somebody is interested in seeing actually the code. But it's how you can see here. It's actually, of course, it can be used for classification models.
Yeah, Pablo. And because it's primarily depend on the type of model and the inputs that you're feeding, so you should be able to use it. Francis has a question as well, which says, how does, I think it generally comes up when we talk about SHAP. So how does SHAP compare with LIME?
Okay, nice question. So actually, to understand SHAP, you need to understand both the Shapley values and LIME. The difference with LIME would be that LIME is more as a local explanation method, and SHAP kind of generalizes that. I think somewhere that is very well explained is in the, let me have some resources here. So in the interpretable ML book here, there are 3 chapters, actually, one for Shapley values, another one for Lime, and another one for SHAP. And it clearly states the difference in a very, in a very nice way. But that would be the main difference, yeah.
Yeah, awesome. Thanks, Maria. So there's lots of questions flowing in, actually. It's a hot topic. Next question is from Anita. So the question is, how would you calculate the trustworthiness based on functionality, explainability, and robustness? Would you create an index score?
Okay, yeah, so to have an actual number for functionality is basically what we all do every day. So you choose your measure, and then you will have like the number of the score of the accuracy, the F1 score, the coefficient correlation, or whatever you're using. For the robustness pillar, it's also easy kind of to get. So usually what you can do is that you attack your model, and then you get then you compare the difference between the accuracy or whatever measurement of the performance you are using before and after the attack. And so with that difference, you get a number. And if you actually want to perform different attacks in the same model, what you can do is create like a key robustness indicator, what we call it at my startup. And you would just like compute like a pondered sum of all these differences. Then for the explainability pillar, it's a little bit more complicated, because of course you can see them, like if your model is explainable or not, but there are actually some measurements you can do. You can measure the fairness, for example, and there are a lot of different ways to define this as a formula. But the idea is to just have some kind of combination of these 3 scores, and then just set a threshold, like whatever you want, like 0.8 out of 1 or something like this.
Awesome. Thanks, Maria. And Tina has a question that seems to be along the same lines, which is, in the last slide, you proposed that you combine 3 metrics. Any suggestions on how you can combine them, and the use cases for the model, which might change the weighting for each? So I think he focuses, or he or she focuses more on how to combine them. And you mentioned you can combine them with some weights. And I guess the question is, how can you come up with those weights?
Then of course it depends. It's a little bit of a trade-off, because usually it's easier to explain models that are less complex, for example. So if you make them less complex, then maybe you're going to lose a little bit of accuracy. But I think this is kind of the famous variance trade-off that we used to have. Now still a problem, but less important. So this would be actually how important is for your use case that the model is explainable. For example, if it's for an automated car, maybe you want it to be more robust than explainable. And if it's for a healthcare, or you want investors or something like this, then maybe you need the explanations to be more important. So it really depends on the use case.
Yeah, I 100% agree. There's one more question for Karthik, and which is, how do we think about explainability for multitask or multimodal ML models? I kind of asked Karthik if he could expand a bit. Karthik, do you want to unmute yourself, expand a little bit, or maybe chat and expand a little bit, please? Oh yeah, so he's saying for models that use tabular plus text data, like if they use multiple different types of data in the same model, how would these 3 pillars work? Like how would we construct the functionality, explainability, and robustness in that case?
Okay, so to be honest, I've never had a use case like this, so I don't speak from experience here. But Actually, when you are just measuring the functionality, you usually have different metrics. So you would have one for the tabular part and then another one for the text. So the idea would be to actually do the same thing for the explainability part and also the robustness. So yeah, for the explainability, I think it's easier to just combine them, because at the end, they're just like the explainability plots just map the input features to the output. So it doesn't matter which kind of input feature you have. But for the robustness, the attacks are really different for the type of data you have. So you would have to perform one for one thing and then another one. So yeah, kind of try to separate it, I think.
Okay.
But it's actually a nice question.
Yeah, it's also it's also an interesting one, because I feel like that'll be the next step, right? Like once you're able to explain these kinds of models, and the next step is,
Yeah.
because I think that follows from the next question that Will has, which is, how would explainability work for ensemble models? Would you try to explain each model separately or all as a whole? How would that work?
Yeah, so you can actually do both. You can have saliency maps for each of your models, and then just check if, individually they are all explainable, or maybe you just have, some kind of bias in one of them, but not in, if you do the average, then you wouldn't see it. But then, of course, at the end, we want our final model to be explainable or robust or performant. So yeah, the idea, I think, like if you want to really just check at the end, like this additional step before deployment, then I would definitely check for the whole the combined
Awesome. Well, I hope that answers your question. And I think there's no straightforward answers to any of these, right? It's a lot of them are, you have to experiment and see what makes sense for your use case. So Yash has another question, which I think kind of leads into the question I had as well, which is, he's asking about explainability's role in auditing and compliance. And I want to add to that to ask a little bit about what neurocat does, which is, because I saw your mission and it says safe and secure AI usage for industry and society. Which seems like a fantastic but very hard mission. So I'm curious to understand and maybe also kind of touch upon the role of that in auditing and compliance. Like how does, what is the work you're doing, and how does it fall into this trustworthiness space?
Yeah, sure. So what we are actually developing is aidkit. It's called aidkit, and it's an assessment tool for the quality and trustworthiness of the models. So basically, what we have is we separate our toolkit into 3 categories, the same way I have separated my talk, so into functionality, explainability, and robustness. And then we provide some saliency map and explainability techniques to explain the model of our clients. And then we also provide custom attacks to, so we can, for example, we use attacks from the literature, but also custom attacks that are specifically for the data of or the use case of our clients. And then we use that, it's like a web app, or you can also access it from the CLI. So it's just you install a pip package, and then if you have this license, you can just make API calls and you get reports about how trustworthy your model is. So that, of course, can also be used for consultancy and other type of projects.
Awesome. Very, very fascinating, because I feel like this is almost the future. Like, I think the previous era focused a lot on scaling and building more complex models and getting more accuracy. But I think the tide's turning now, where everybody wants to know what AI is doing. So I think it's great work. We have one more question, which is from Vance, which asks the question, who asked the question, SHAP can help explain or interpret models on a per feature basis, or per data point basis, I guess. But in your experience, how do we know if SHAP output is good enough? Or how can we say a model is trustworthy? This is the cyclic question, right? So
Yes, yes, yes. Actually, it's actually a very good question, because of course it depends. Like if you are trying to explain a white box model, so if you have access to the gradient of the model and all these kind of numbers in the middle, it's a little bit easier to know if you're actually explaining it well. But if you try to explain a black box model, then yeah, there's actually no way to know if the explanation is actually correct or not. And yeah, a couple of days ago, preparing the talk, I found a really short paper that I think I also have here. Yes, so it's like a 5 pages thing, and the title is "The Myth of Complete AI Fairness." And basically, the first sentence says that we are never going to trust AI 100%. Yeah, but let's try at least.
yeah, just to add to that, I guess you rely on the math, right? Like if you get to the math, you kind of understand the math is
Yeah.
sort of correct. You almost know that all SHAP is trying to do is try to perturb a few things and try to see what the outcomes are and just measuring that. So yeah, it's a very good question, and I don't think anybody can answer that straight up.
Yeah.
Victor has it. Oh wow, this seems to be a really popular chat. I've never seen it go up so much. So Victor has a question. I wonder how model trustworthiness translates to model drift. Deployability criteria are often not scalable to monitor in real time. Would you adjust these pillars after moving it into production setting to continue monitoring trustworthiness?
Yeah, so I think the most important check is kind of so before it gets into production, because then sometimes you just deploy a model and a couple of weeks after, then there's just like horrible news. This model is super biased, or so the idea is to avoid that to happen. But of course, if you're retraining your model and you're doing like CICD, then yes, it would be nice to also update the scores. But for example, you can actually like have a also like update the weights of your final score, or make it a little bit lower. But I think really the most important thing is make sure that when you deploy it, it's as explainable and robust as possible.
Awesome, awesome. So I guess we're done with our questions. And I think we're also out of time. So thank you, everybody. Thanks to everybody for showing up. The audience makes the talk. So thank you, everybody. And of course, Maria, thanks for the fantastic talk and a really, really great topic. I feel like I'll see you more and more because you work in this space. I feel like you'll be invited to many more sessions to provide your insights on this topic. So thanks, everybody. And of course, there are many, many more sessions that are happening in parallel this afternoon, tomorrow. So I hope to see all of you there as well. So thank you, Maria, and thank you to the audience as well. Bye.
Thank you very much. Bye-bye.